Okay, thank you. Thank you, Daniela, for your kind introduction and for your help. Ladies and gentlemen, good morning. My name is Andrea Zanichelli, and today I'd like to present to you the second part of this research work carried out within the project of great national interest related to the formulation of innovative methodology to design, you can see here, metallic additive manufacturing complex components for civil engineering structures subjected to time-varying loading. So first of all, I would like to thank my co-authors from the University of Parma. And so this contribution deals with the validation of the analytical methodology already detailed by my colleague Camilla in the previous contribution. This methodology, as you already seen, allows us for the fatigue assessment of notched components made of additively manufactured metals, and it is here applied to a comprehensive experimental campaign that we carried out on notched specimens made of titanium, aluminum, vanadium, and which is obviously taken as the basis of the methodology validation. So my presentation consists of the following sections. After a brief introduction in which I will recall the main aspects of the methodology, I will describe the experimental campaign carried out for the methodology validation, particularly focusing on the findings that will serve as input data for the methodology itself. Then I will show the results obtained when applying the methodology to the above experimental campaign before moving on to some conclusions. So very briefly, the analytical methodology proposed is based on the joint application of the multi-axial fatigue criterion proposed by Carpentieri and the Taylor's point method. The novelty of this methodology lies in the definition of the critical distance, that is the identification of the critical point, P critical, where the fatigue criterion is applied. So this critical distance is a function of these four factors, mainly, that is the control volume radii provided by the said criterion, and that are computed accounting for material porosity, the biaxiality ratio, the ratio between the fatigue strength of notched specimens under Mod 3 and Mod 1 loading, and the surface roughness. And here you can see the expression for computing the critical distance RAM. And of course, it is function of R1, R3, that are the characteristic length of the said obtained by according to the said approach. These lengths are determined through either closed form expressions for V notches or numerical simulations, but in both cases they are function of sigma 1a and tau 3a, that are the fatigue strength of smooth specimens under Mod 1 and 3 loadings. And here, in order to compute sigma 1a, we employ the model proposed by Alves et al., which gives this value as a function of the weaker hardness and the maximum defect size of the material. Then, since we didn't find any analogous relationship in the literature for the Mod 3 values, tau 3a is conservatively assumed equal to the corresponding value of sigma 1a, based on the experimental observation that for, at least for additive manufacturing T6AL4V specimens, tau 3a is comparable to or even slightly higher than its actual fatigue strength. Then, RAM, as you already see, is a function of the biaxiality ratio, tau A is over sigma A, and of the ratio between the fatigue strength of notched specimens in Mod 3 and Mod 1 loading, and of some surface roughness measurements. So here are the main steps of the methodology proposed. I will go very quick again here because you already seen these steps in the previous contribution. So we have some input data to be set that are these ones here. Then we define the critical distance RAM by employing the equation in the previous slide. Then by means of this value, we identify the critical point at a distance half of RAM on the notch bisector line. And at this point, we compute the stress field, we determine the critical plane orientation, and we perform the fatigue assessment by means of the Carpentieri et al. criterion. So let me now describe to you the experimental campaign carried out on additively manufactured specimens. In particular, we employed the electron beam powder bed fusion process to fabricate the specimens, and a titanium 6 aluminum 4 vanadium powder is used as a fixed stock material with particle sizes ranging from 45 to 106 microns. The details on the powder composition are shown here, as well as the main process parameters. And let me say that with these process parameters and with the high build temperature, a high dimensional accuracy is ensured, the residual stresses are eliminated, and so we didn't need any post-processing heat treatment on the specimens. So, first of all, fatigue tests have been performed on cylindrical notched specimens. 3 different notch geometries are considered, as you can see on the right of the slide. So we have a sharp V notch with a notch depth of 2 millimeters, an opening angle of 90 degrees, and a notch root radius of 0.07 millimeters. Then we consider a circular notch with a notch radius of 2 millimeters. I will call it C2 notch later, and a blunt notch with a notch radius of 5 millimeters that I will call it C5 notch. So, uniaxial, both axial and torsional, and multi-axial fatigue tests are carried out under load control at a frequency of 15 Hz with a stress ratio of -1. And for mixed mode loading, proportional axial and torsional loads are applied with a constant biaxiality ratio. So firstly, we determined the SN curves for each notch configuration for both mode 1 loading and mode 3 loadings. And as you can see here, I show the curves together with the expression for both mode loadings. Relatively to mode 1 loading, we notice that the sharp is the notch, the lower is the curve, whereas in case of mode 3 loading, we obtained similar curves for all the notches configuration. And relatively to the slopes of these curves, we obtain quite similar slopes for each notch configuration in mode 1 and in mode 3 loading. Then, in order to apply the analytical methodology proposed, some additional input data are needed. So we performed tensile tests on 3 smooth specimens. You can see the geometry of the specimen here and the stress strain curves obtained in this graph. And the experimental tensile strength obtained is 875 megapascal. Then we analyze the surface roughness by means of a Leica system with a 2 millimeters evaluation length used for the measurement. We obtained a total height of the raster profile RT equal to about 130 microns, and the maximum valley depth value equal to about 66 microns. And then a defect content analysis is carried out by means of a statistical method based on the well-known extreme value theory. We perform this analysis on the data from a cross-section perpendicular to the longitudinal axis of the specimen. And here we notice that both pores and non-metallic inclusions are present, but since the inclusions are up to 4 orders of magnitude smaller than the pores, only the pores are considered in the statistical evaluation. And thus, we obtained a value of the square root of the maximum defect size equal to about 250 microns. And finally, the Vickers hardness is computed by obtaining the value reported here. And by employing these 2 values, so the Vickers hardness and the maximum defect size, we computed the fatigue strength of smooth specimens for mode 1 loading by employing the model I showed before, by obtaining a value of about 105 megapascal. And then we conservatively assume the value for mode 3 equal to this one. So now that we have all the data necessary for the application of the analytical methodology, we can see the results. And in this slide, the results related to the sharp V-notched specimens are shown. At the top, you can see the said control volume characteristic length. And then by means of the equation shown at the beginning of this presentation, we computed the critical distance with this value here, obtaining a very small value of 0.03 millimeters for mode 1 loading and about 1.5 and 0.2 millimeters for mode 3 and mixed mode loading. And then, as you can see, at least for this case here of sharp V-notch specimens, the methodology is able to capture the runout that we found experimentally, except with the only exception of one case in mixed mode loading, in which the methodology provides a non-conservative estimation of a runout for a specimen that actually broke during the experimental campaign. Then, moving to the results related to the C2 notch specimens, also here you can see the values of the critical distance we compute for mode 1, 3, and mixed mode loadings. And as you can see, higher values are obtained in this case with respect to the V-notches case, especially for the mode 1. We had 0.03 millimeters for V-notched, and we have here 0.4 millimeters for this case. And well, for the circular notch specimens, the methodology provides more conservative estimations, especially in the case of the runout tests. And then the results for the C5 notch specimens that are in line with the C2 ones, since we have similar values of the critical distance, again, higher than the case of the V-notch specimens, and again, conservative estimations, especially in the case of the runout tests. So here you can see the comparison between the experimental results in terms of fatigue life with the theoretical ones. In this graph, the scatter band of 2 and 3 are shown with the dashed lines and with the dot dashed lines, and as you can see, we obtain quite good results, especially in the case of the C2 and C5 notch specimens, since all the results for at least within the scatter band 3. Whereas in the case of the V-notch specimens, we have some outliers, 2 here and 1 here. This is also due to quite scattered experimental results that actually we obtained during the experimental campaign and during the fatigue tests. But we still have quite good results, as highlighted by the TRMS values. It is likely higher than the case of C2 and C5 notches. It is instead very, very good and similar to each other. Then, finally, here we can see the comparison between the orientation of the critical plane calculated by means of the methodology and the final fracture plane that is experimentally observed post-mortem on the specimen tested. So for mode 1 loading, we can see in red the calculated orientation. So for mode 1 loading, we have a critical plane perpendicular to the longitudinal axis of the specimens. This plane becomes with an orientation of 45 degrees with the longitudinal axis of the specimens in case of mode 3 loadings, and both these values are the same for all the notches configurations, whereas in mixed mode loading, we found an orientation equal to 56 degrees for V-notch, 60 degrees for C2, and 61 degrees for C5 notches. And let me say that all these results are in good agreement with the experimental observation of the final fracture plane of the specimens. So let us move to the conclusions. In the present paper, an analytical methodology for the fatigue assessment of additively manufactured metallic notched components has been validated through a comprehensive experimental campaign carried out by the present authors on notched additive manufacturing, titanium, aluminum, vanadium specimens. In particular, such a methodology is based on the joint application of the Carpenteri criterion and the Taylor's point method, and takes into account the surface roughness and the material porosity for the definition of the critical distance. The results obtained are in good agreement with experimental findings in terms of both fatigue life and final fracture plane, regardless of the notch configuration and the loading time. So on the basis of the results obtained, it can be concluded that the proposed methodology can effectively capture the interactions among the various parameters influencing the fatigue behavior of additively manufactured notches components, thereby serving as a reliable and robust tool for their fatigue design. So thank you for your kind attention.